So we just went through aliasing when it arises, how it's related to Nyquist rates and Nyquist frequencies. So what we're going to talk about now is how to avoid aliasing, right? Because we want to avoid it because of all the problems that it might create. Okay, so there's kind of two approaches we can use to avoid aliasing. The most obvious is to say that if we know what the fastest frequency sinusoid is in our signal, right? So fastest sinusoid, then we just need to make sure that our sampling rate is above the Nyquist rate, right? So we want to make sure that our sampling rate is greater than 2 times that fastest frequency. Okay, and and then as we just showed in that demo, is that we really want this to be considerably larger than this Nyquist rate, so we don't distort the amplitude of that signal, right? As long as we choose the sampling rate, we'll avoid aliasing, but if we are just here, we might distort the amplitude and what the actual shape of that signal looks like. Okay, so this is the easiest way to avoid aliasing, right? We know the frequency, the fastest frequency in our signal, just choose our sampling rate accordingly, right? But like now what happens, let's say that we don't know our fastest frequency, okay? Or let's say that we do know the fastest frequency, but the nature of our hardware is that we actually can't choose the correct sampling rate, right? For whatever reason, our A to D card can't be specified, or we can't specify a rate such that it avoids aliasing. So what do we do in that situation? So it's a relatively simple solution for this. And basically what we're going to do is have what we're going to call an anti-aliasing filter. Okay? And this name doesn't really tell us anything special about the circuit we're going to use. It's just kind of saying what the function of this filter actually is, right? And in practice, you've seen this before. All it is a low-pass filter, right? So the idea here is that what we want to do is create a filter, a low-pass filter, which passes a bunch of the frequencies within its passband, right? So this again is our kind of amplitude response, right, and against frequency. So the amplitude of our signal is a function of the frequency. And we want it to pass a bunch of frequencies for the low frequencies, low-pass filter. What we want it to do is then suppress frequencies that might cause aliasing, right? So the idea is that we have a signal, let's say our blood pressure in our example before, which has high frequencies that might cause aliasing if we sample it at too low of a rate, right? So we can't change the rate to avoid aliasing. So what we want to do is filter that signal so we suppress all those high frequencies components of our signal and therefore avoid aliasing before even sampling, right? So basically get rid of any possible aliasing and then we sample it after the fact and we know we've avoided it. Okay, so clearly we have a low-pass filter and we want to choose our cutoff in some relationship to the frequencies that will cause aliasing, the Nyquist frequencies, right? So we've got some sort of a cutoff here, WC, okay? So do we want to choose WC to be equal to our Nyquist frequency, which would be 1/2 of our sampling rate, okay? So let's say we do that. So then any frequency from here forward could potentially cause aliasing, right? Okay, so we could do that, but this really won't prevent aliasing, right? Remember that for a low-pass filter, especially for a Butterworth filter, which we've been working with, when you're at the cutoff frequency, it only drops by 3 decibels, which corresponds to 1/2 of the input voltage, okay? So again, if we have our blood pressure example, we've got our blood pressure signal, and we've got a high-frequency signal on top of it, this low-pass filter is only going to suppress that high frequency by about 1/2, okay? So what we want to do then, instead of choosing it, we don't want to do this. What we want to do is choose our cutoff frequency so that it's less than our Nyquist frequency, okay? So what we want to say is that if we want to choose our filter, okay, and choose the cutoff, and choose here, WC, again, decibels versus frequency, okay? We want to choose the cutoff so that when aliasing starts, let's say aliasing happens for all frequencies above here, right? So this is all bad region. By the time our filter gets to these frequencies, it's already suppressed our signal quite a bit, right? Suppressed those frequencies quite a bit so that they're removed, right? So if we only have it here, there can still be those high frequency aspects or components to our signal which can cause aliasing. So instead we want to choose a cutoff frequency that's well below our potential frequencies that could cause aliasing. Okay, so these are approaches that you're going to use, that you want to use, to avoid aliasing in practical circuits. And in many cases, when you're running experiments or collecting data or taking measurements of things, you want to be really aware of this. And you'll see often people with anti-aliasing filters just as part of the basic circuitry when they're making measurements, right? Just trying to say, well, I don't really know much about the signal that I'm sampling. I don't know the fastest frequency, but I do know the sampling rate that I have. So I'll put an anti-aliasing filter to get rid of those higher frequencies, just to avoid aliasing, so I know there's no contamination. I might lose information that's at those high frequencies, but I'd much rather lose that information at those high frequencies than have those high frequencies alias as a low frequency, right? Because once that aliasing occurs, I've completely corrupted the signal that I'm interested in, corrupted the signal that I'm actually measuring. Okay? So these are the strategies that you can use to avoid aliasing.